Okay, so in this section we are going over maximum and minimum values. So we're going to see, not in this section, but in future sections, a type of question called optimization. And this is going to involve finding the optimal way to do something. So for some examples, we have what is the shape of a can that minimizes manufacturing cost? What is the maximum acceleration of a space shuttle? What is the radius of a contracted windpipe that expels air most rapidly during a cough? And at what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? So these are just several examples of what we call optimization problems. And what these problems actually are doing is we are finding the maximum or minimum values of a function. So let's start off with what we actually mean by the maximum and minimum values. So starting with the absolute maxima and this should actually say the absolute minima. And typically I just tend to call these absolute max, absolute min, just to abbreviate. So if we're looking at this graph down here, we can see that the largest value of the function is f of 3 equals 5, right? Because that's just the largest y value for the function. And we can also see that the smallest value of the function is f of 6 equals 2. So what we would say is that f of 3 equals 5 is the absolute maximum, and f of 6 equals 2 is the absolute minimum. So overall, this concept hopefully is pretty simple. The absolute maximum value is just the largest y value on the graph, and the absolute minimum value is just the smallest y value on the graph. Okay, so also these are both called extreme values of a function, and we're going to see in a couple examples here that a graph may or may not have an absolute maximum or an absolute minimum. Okay, so the next type of maxima and minima are relative maxima and relative minima. So a relative maximum point, so another word for relative is local. So if you see the word local maximum, it means the exact same thing. So a relative maximum point is going to be a value at which the function has a larger y value than the points directly to its left and directly to its right. So it's higher up than the points directly next to it. It may not necessarily be the largest point on the graph, but it's larger than the point directly to its left, directly to its right. Same idea with a relative minimum or a local minimum value. It's going to be a value where the function has a smaller y value than the points directly to the left and directly to the right. And just like we saw with the absolute, these are called relative extreme values for a function. And we do just have to be a little bit careful because they cannot actually occur at endpoints of a function. So sometimes these will be very easy to spot if the function is nice and continuous, maybe even smooth and continuous, meaning rounded turns. Then whenever the function changes from increasing to decreasing, we can see that there is a relative maximum value when it changes from increasing to decreasing. Similarly, if it changes from decreasing to increasing, we can see that there is a relative minimum value when it changes from decreasing to increasing. And here's just an example of a graph where it has a little bit of everything here, where we have absolute and relative max and min values. We can see that right here, f of a is the absolute minimum, and f of d is the absolute maximum because those are the lowest and the highest y values on the graph. But then we also have relative max and relative min. We have a relative max right here at f of b, and we have, it looks like that is one of two relative max. Another relative max is actually the same as the absolute max for f of d. And then for the relative minimum values, it looks like we have a relative minimum value at f of c. So all of these are listed right here, and I just filled them in on the graph. Oh, I missed one. There is also a relative minimum at f of e as well. So sometimes these are a lot easier than other times, but each function can have none or one absolute max and absolute min. But for a relative max and relative min, it could have none, it could have one, or it could have multiple relative max and relative min. So let's start with a nice easy one where we have a function. Sometimes we'll be given functions, sometimes we'll be given graphs. Determine the absolute max and min and the relative max and min for f of x equals x squared. So we should all know what this looks like, right? This is our basic parabola. And we know it looks something like this right here. So if we want to find, let's start with the relative maximum point. There is no relative maximum point here. It never changes from increasing to decreasing. So there is no relative max. For the relative min, there actually is a relative min right here at the vertex because it changes from decreasing to increasing, and that's going to be a point that's smaller than the points directly to its left and directly to its right. So there's a relative min at the coordinate 0, 0. So sometimes questions will be asking you to find these points. If it says to find the value, value would mean y value. I'm just writing these as xy ordered pairs for now. All right, next onto the absolute extreme. So we have the absolute max. There is no absolute max because the arrows are going to infinity. So there is no absolute maximum. And for the absolute minimum, the smallest y value on the graph, once again, is going to be the same as the relative minimum. That's at the point 0, 0, right at the origin. So that's an example of probably an easier case. So let's see another example where we have another graph for us. So determine the absolute max min and the relative max min for this function f of x equals 3x to the fourth minus 16x cubed plus 18x squared using the graph that is given to us. So let's start with the absolute. I didn't write it in the order that I'm going to do it. But let's start with the absolute max and the absolute min this time. It looks like the largest point on the graph is right here at -1, 37. So the absolute maximum point is the point -137. And remember what I said before, if the question's asking you for the value, then, which it is, so I guess I should take that into consideration right now. If it's asking you for the value, it wants the y value. So I'm going to write this like this. The absolute max is f of -1, which is 37. That way, technically we're given the x value as well, but f of -1 is the y value, which is 37. Okay, so for the next one, let's do the absolute minimum. The absolute minimum, the smallest point on the graph is right down here, and that is the coordinate +3, -27. So the absolute minimum value is the y value, which is -27. And now for let's take a look at any relative max. This function is smooth and continuous over this interval. So it looks like it's usually pretty easy when it's smooth and continuous. It's changing from increasing to decreasing at the point 1, 5. So the relative max is f of 1, which is equal to 5. And you can just tell that it's larger than the point directly to its left, indirectly to its right. And then lastly, for the relative minimum, we have two relative minimum points. We have, it looks like at the origin, so f of 0 equals 0. And we know that that is a relative minimum because it's small, the y value is smaller than the y value directly to its left, directly to its right. And then we also have one here, which just so happens to be the absolute minimum as well. And that's the coordinate 3, -27. So the value is -27. All right, so on to another example, and this one can get a little bit tricky. Where we're given this graph, we can see that there's jumps here, there's holes, and let's figure out the relative max and min and the absolute max and min once again. Okay, so maybe let's start with the absolute max. It doesn't matter where we start, let's just start with the absolute max. The highest point on the graph looks like it's right over here. That's the largest y value. And it looks like that has an x coordinate of 6. And the y value is 1, 2, 3, 4, 5. So the absolute max is f of 6 equals 5. And just for spatial reasons, I'm just going to write this as 5. So the absolute maximum value is just 5. Okay, next for the absolute minimum value, this is where it gets a little bit tricky. The first one's hopefully pretty easy. Now it gets a little bit tricky. It looks like the smallest y value is right down here, right at that where that hole is. Except since there's a hole there, the function actually doesn't exist there. So it gets infinitely close, like it looks like it's almost going to be -3, but it gets infinitely close to -3, but it actually doesn't reach it. So that means that there is no absolute min. So if the highest point or the lowest point is a hole, then that means there would not be a absolute max or an absolute min at that point. All right, so that's the first tricky part. On to the next tricky part here. Let's take a look at any relative maximum. Or relative maxima, I should say. So that's going to be, once again, we should say the definition in our head. It's going to have a larger y value than the points directly to the left and directly to the right. So I kind of like to scan this left to right when I do these types of questions. So once we are scanning this, we get to this point right here, the point where there's a hole and then there's another filled in dot for the function. So this is actually a relative maximum value because the function is larger than the point directly to its left and directly to its right at that value. Right, so the value itself is going to be the y value, which is a y value of 2. So that one's kind of tricky. Once again, it's this value right here, this point right here, which is the y value of 2. So we keep on scanning left to right, and we get to this point right here. Hopefully this one's a little bit more obvious, that this is also a relative max, and that has a y value of 3, because that's changing from increasing to decreasing. And we keep scanning and we get to this point right here. So here's the next difficult point for a relative max. If we think about the definition, this point is larger than the point directly to its left and directly to its right. That, because it's a filled in circle, so that means that is a relative maximum value, which is the value of 1. And then we keep on scanning. It looks like there's another one right here. And that's going to be the y value of -1. And it looks like we have one more. So this one right here is not a relative max. It's larger than the point directly to the left, but it's not larger than the point directly to the right. So that's not a relative max, but this one is right up here. It happens to be the absolute max as well, and that is a y value of 5. So there just happens to be several relative maxima for this function. All right, so I'm going to point at all of them. Okay, so all of those arrows are relative max. Now let's look at the relative min, and we're scanning left to right. It looks like we don't have a relative minimum until this value right here, and that's going to be a y value of 0. And we keep scanning left to right, and this is not the one I'm highlighting now. This is not a relative minimum because it's a hole. So if that was a filled in circle and this was a hole above it, then it would have been a relative minimum. So that's not a relative minimum, and that's actually it. There's no more relative min. It's just the y value of 0. Okay, so I'm going to just draw an arrow in a different color. to that relative min value at 0. All right, so that one's the tricky one. So let's move on to a couple other things. The next thing is the extreme value theorem. And the extreme value theorem says that if f is continuous on a closed interval, so just remember that a closed interval means the endpoints are included, which essentially means when we write it in interval notation, they have brackets. If it was an open interval, that means they would have parentheses, meaning the endpoints are not included. Okay, so if f is continuous on a closed interval a to b, then f has to have an absolute maximum and an absolute minimum value at some numbers in the interval a to b. Once again, that's because this is continuous and it is a closed interval. So here are just some examples where all of these functions here are continuous and the endpoints are included, so it's a closed interval. So you can just tell by looking at all of those that the first one will have a absolute maximum there, an absolute minimum there. The next one will have an absolute max there, absolute min at the endpoint, and then the third one has the absolute max at 2 separate points, but it's the same y value, and then an absolute minimum right down there. And then here are some examples where we have to be careful a little bit. This function has a absolute minimum at f of 2, which is 0, but it does not have an absolute maximum value. So the reason why this extreme value theorem doesn't come into play here is because the conditions are not satisfied. F of x is discontinuous, right? We can see that there's that big jump at x equals 1. There's a big jump right here. So that means it's discontinuous. So that's why the theorem does not hold true for this instance. And we can see that it has no maximum value because there is a hole at that value right there. Okay, and then another one that we have to be careful of is something like this. This function is continuous, except it has no minimum and no maximum. That is because it is not a closed interval. And that's because we have a hole at this endpoint, which would have been the absolute minimum. And then we have a vertical asymptote on the right open interval. All right, so let's do maybe one more theorem here, Fermat's theorem. So Fermat's theorem says that if f of x has a relative maximum or a relative minimum at c, and f prime of c exists, that means f prime of c equals 0. So if we know that there's a relative max or a relative min, and the derivative exists, that means f prime of c equals 0. So a lot of the time, students forget about the second condition. That's very, very important, because if f prime of c doesn't exist, then it can't equal 0. So what does this mean? Let's take a look at this graph right here. So we can see that we have these 2 points. We have this point here, c, and the x value of d. So we can tell that there is a relative maximum at c because it changes from increasing to decreasing. And we know just by looking at it that f prime of c exists because this is a smooth continuous function. So that means that f prime of c equals 0. So what does that mean? If we think back to tangent lines, that means the slope of the tangent line is 0. So it is a horizontal tangent line. Okay, and then same idea for the one down here. We have a relative minimum. And once again, smooth continuous function, so the derivative there will exist. So that means, based on this Fermat's theorem, that f prime of c equals 0, which means it is a horizontal tangent line. So we have to be a little careful with this theorem because going the other direction, saying f prime of c equals 0, that does not always mean that there will be a relative maximum or a relative minimum at that value. So for example, if we have the function f of x equals x cubed, if we are told, or we just figure it out, that f prime of 0 equals 0, that does not guarantee that there is a relative maximum or a relative minimum at that point. We'll end up seeing that this will be true a lot of the time. There's going to be a way that we figure it out in the upcoming section. But just because f prime of 0 equals f prime of a number equals 0 does not always mean that it's a relative maximum. And we can tell by looking at it right here. We can tell that this is a horizontal tangent line, but it is not a relative max or a relative min. All right, and then another one we have to be careful of is f prime of x equals the absolute value of x. We can tell, and we should know, that f of 0 equals 0 is a minimum value, right at the origin. That's clearly a relative minimum because it changes from decreasing to increasing. But this does not mean that f prime of 0 also equals 0. That is because f prime of 0 actually does not exist, because there is a cusp at that value. So if there is a cusp or a sharp, remember a cusp is a sharp point, a sharp turn. A cusp means that the derivative does not exist at that point. So you have to be a little bit careful with that theorem. All right, on to one of the last things here, and this is one of the most important things for this section, is critical numbers. We're going to be using this in the upcoming sections as well. A critical number of a function is a number c in the domain of f of x such that either the derivative equals 0 or the derivative does not exist. So that means if we're finding critical numbers or critical values or critical points, I tend to use those terms interchangeably. If we're finding critical numbers, we have to find the derivative, set the derivative equal to 0, and then solve for x. Or we can also find the derivative and then find when the derivative does not exist. So we cannot forget to do this one right here. A lot of the functions that we're going to be dealing with, maybe the like a polynomial, for example, the domain of the derivative will be all real numbers, so we don't have to worry about that, but don't forget about it. Sometimes it will come into play. So let's see a few examples. And for this one, we want to find the critical numbers of f of x equals x to the 3/5 times 4 minus x. So we know that to find the critical numbers, we need to take the derivative, set the derivative equal to 0, and also see if the derivative does not exist for any of the x values. So the derivative here, f prime of x, we have two options technically. We could distribute and then take the derivative using power rule, or we can just do product rule right away. I guess I'll just do product rule right away. So we have our two separate functions being multiplied. So first times the derivative of the second plus the second times the derivative of the first. And we can simplify that a little bit as negative x to the 3/5 plus, I'm going to write the second term as a fraction here. So 3 times 4 minus x divided by 5 times, and I'm put this as a negative exponent. I'm going to make it positive by putting it in the denominator. Okay, and then the next step, this is where it gets a little tricky. So we could try to take this into account right now and set this equal to 0 and solve, see when it does not exist. A lot of the times when you're dealing with these types of functions, it is good to just get common denominators right away and then worry about solving these on the left here. So let's get common denominators. And I'm just going to show my work on the side, I guess. The common denominator, the least common denominator would be 5x to the 2/5, which means we have to multiply that first term by 5x to the 2/5 divided by 5x to the 2/5. We have to multiply that in the numerator and denominator. And this numerator actually simplifies kind of nicely. Remember, when we are multiplying common bases, we add the exponents. 3/5 plus 2/5 actually equals 1. So that one's kind of nice. The denominator, we have the common denominator that we wanted. 5x to the 2/5 plus that second term. And since we just got the common denominator, the whole point of doing that is to combine them into one fraction, right? So combining these into one fraction, I'll leave it to you guys just to check. Distribute this 3 and then combine like terms with that first term's numerator. And we would end up getting the derivative is 12 minus 8x over that common denominator. All right, so there's the derivative, nice and simplified. And let's go ahead and find the critical values now, the critical numbers. And to do that, we have to do two things. We have to find when the derivative equals 0, and then when the derivative does not exist. So this is kind of nice now when it's simplified. The only way that this whole thing is going to equal 0 is if the numerator equals 0 only, right? Anytime you have a simplified fraction, the only way it equals 0 is if the numerator equals 0. So solving this for x, because it's a nice little linear equation now, we can add 8x to both sides, divide both sides by 8. Simplify 12 divided by 8 is 3/2. So this is one of our critical points. Now to find when the derivative does not exist. This particular derivative will not exist when the denominator equals 0. So we set the denominator equal to 0 for this one. And you could divide both sides by 5 and then raise both sides to the 5/2 power. But hopefully you can tell by looking at it, if you do all that work, you're still going to get x equals 0. So in the upcoming sections, we're going to go a step further after finding these critical values. But I put the graph on here. You can tell by looking at the graph that at x equals 3/2, which is 1/2, there is a relative max at that point. At x equals 0, there is a vertical tangent line. It's kind of hard to tell by looking at the graph, but there is a vertical tangent line right here. So that would mean the derivative does not exist with a vertical tangent line. Okay, so we found our two critical numbers. All right, so for the, I believe this is the last, this is the last page here. Let's find the absolute maximum and the absolute minimum of a function. And for this method, this is going to be the closed interval method, which means we're going to have our endpoints included. So we have the brackets, closed interval, endpoints are included. So we just have to do a few steps. It's actually relatively straightforward. We do also have to keep in mind that this method here is for a continuous function on the closed interval. So I'll highlight these because that's very important, because obviously not every function or question will satisfy those conditions. All right, so first step is going to be find the critical numbers, just like we just did. So we're going to take the derivative, find when the derivative equals 0, find when the derivative does not exist, just like we did in the previous example. The next step is we're going to find the values of the endpoints of the interval. So that's just finding, if we're using the interval a to b, that's just evaluating f of a and f of b. No calculus involved there, just evaluating the endpoints in the function. And then step 3, well, actually I skipped over a part in step 1 here. For step 1, going back to step 1, we find the critical numbers, but we also have to evaluate the function at those critical numbers. So find the critical numbers and then evaluate f of those critical numbers, and then the order doesn't actually matter, and then find the function evaluated at the endpoints. Once you have all of those, the largest of the values out of all of those is the absolute max. The smallest of those values is the absolute min. All right, so let's see one more example here. And we want to find the absolute maximum and the absolute minimum values of f of x equals x cubed minus 3x squared plus 1 on the interval -1/2 to 4. And then we're just going to use this graph here to help us verify this in a second here. So technically, I'm going to do what the steps said. I just like to think about it a little bit differently. I like to start by just writing this because this is kind of the whole point of it. Evaluate f of x at the endpoints and the critical numbers. So we already have, the reason why I kind of start here is because you're always going to have the endpoints. So we need to evaluate f of -1/2 and f of 4. And to do that, we just plug them in the function, right? So -1/2 cubed minus 3 times -1/2 squared plus 1. And simplifying that and getting common denominators, we end up getting 1/8. Next, plug in a 4. 4 cubed minus 3 times 4 squared plus 1. And evaluate that, and we get 17. So there's the endpoints portion, but now we need to find the critical numbers and then evaluate the function at the critical numbers. So we know critical numbers, we take the derivative, set it equal to 0, and solve. Also see when the derivative does not exist. So we have the derivative, and that's going to be nice and easy because this is power rule and the constant rule. So 3x squared minus 6x. And we're going to do two things with it, right? We're going to set it equal to 0, solve it, also see when it does not exist. So setting it equal to 0, 3x squared minus 6x equals 0. This is a quadratic equation. We can factor out a 3x. We'd be left with x minus 2. Set both of those factors equal to 0 and solve them separately. We get x equals 0 and x equals 2. So that's the first part for the critical numbers. The second part is f prime of x not existing. What values of x will make this not exist? The derivative, which we just found, is a polynomial, right? Polynomials, the domain for polynomials is all real numbers, so the derivative will never not exist. So anytime we have polynomials, we never have to worry about the derivative not existing, which is pretty nice. It makes the question a little bit shorter. So all we have to do now is take these critical numbers and evaluate them in the function to find their y values. So we were going to find f of 0 and f of 2. F of 0, plug that in, 0 cubed minus 3 times 0 squared plus 1. That gives us a value of 1. Plug in 2. 2 cubed minus 3 times 2 squared plus 1. And that's going to give us -3. Okay, so now we can just compare and see which values are the largest, which value is the largest, which value is the smallest. That will be our absolute max and our absolute min. So obviously our largest value here is 17 and our smallest value is -3. So that means the absolute, I'm just going to abbreviate, absolute max is f of 4 equals 17. And the absolute min is f of 2 equals -3. And then of course, I just included the graph here for us, just so we can verify that. And you can tell by the graph, obviously, that we are correct. Absolute max and the absolute min over that interval. All right, so that's it for this section. Absolute max, absolute min, and how to find them. Relative max, relative min, and critical numbers. So we're going to pick up with this stuff again in upcoming sections as well.